Alright, ladies and gentlemen, welcome back. In this video, we're discussing circular motion for physics and honors physics. This matches with section 6.2 in your textbook. So, before we get into things moving in a circle, I want you to think back and recall a couple things about Newton's laws of motion. And what the laws of motion tell us about forces and moving objects. So specifically this is going to be related to the first law of motion and the second law of motion, although we do have to also kind of tie this into the third law later on. First law of motion, just a quick recap, basically objects keep doing what they're already doing. So you can think of this as the law of inertia. And inertia, we haven't gotten into this really, but inertia is actually measured by the mass of an object. The more mass an object has, the more inertia it has. And in other words, the more tendency it has to keep doing what it's already doing. If an object is sitting still, it will tend to keep doing that until an unbalanced force acts on it. If an object is moving, it'll keep moving at the same speed and in the same direction until an unbalanced force acts on it and changes that. So that's the first law. The second law, in a nutshell, is really an equation, just F equals ma, one of the most famous equations there are. So with the second law of motion, if there is an unbalanced force, so really we can write net force, acting on some object that has mass, then that unbalanced force produces an acceleration. So conversely, we can say if there's no net force, then the acceleration will be zero. Okay, so if acceleration is zero, then what does that really mean? So we have a situation with no acceleration, speed will be constant. And when we're talking about an acceleration, what it really does is it is the rate of change of velocity. So velocity has two parts. It has speed, but it also has direction. If you are not changing the velocity, or the rate of change of velocity is zero, so your acceleration is zero, then you must be keeping the speed constant, but you also must be keeping the direction constant. Both of those must be true. And so this is interesting. Now we can consider something moving in a circle. And so imagine something tied on a string and you swing it around. Okay, that's easy enough. So I'll try to draw something real quick for you here. This is a diagram you're probably going to see me do a couple times. So let's say you have something tied on a string and you're holding it and you swing it around. Ew, that's a terrible circle, but you get the idea. And so we get this motion, and we have an object, this ball or whatever it is, moving in a circle. So the idea is we want to ask ourselves, well, what's going on here as it moves in the circular path, right? Can we say that the speed is constant? Well, sure, it can be a constant speed. Let's say that it is. Let's just go with that. So we can sort of put a check mark there. Speed is going to be constant. And in fact, for all of these situations we will consider in this part about circular motion, we will say that the speed will be constant. If we're changing the speed, then things get quite a bit more complicated. And we're not going to be dealing with those situations. But clearly, even though speed is constant, the direction is continually changing. Look, right here, this object is moving in that direction. When it gets over to this location, the object is moving in this direction. When it gets over here, the object is moving in this direction. And so the direction is constantly changing. So no, the direction is not constant. Aha, what does this mean? Well, we've got to just look back at the previous line here. If direction is not constant, then velocity cannot be constant. The velocity must be changing. So if direction changes, velocity is changing. If you have a delta V, then there's an acceleration. Absolutely, without a doubt. So because direction is not constant, direction is changing, then the acceleration is not zero. And this is something that, sometimes we don't easily recognize in everyday life. That we can keep the speed of the object constant. It can be a constant speed as it moves around the circle. But while it moves in the circle, its direction is constantly changing, so there must be an acceleration. Must be. It absolutely is there. Now, the final tie-in. And this goes back to Newton's second law. If there is an acceleration, if the object is accelerating, then there must be a net force acting on that object. That force must be there to produce that acceleration. So that's really the gist of what we're going to be getting into here, the nuts and bolts. So let's look at this a little more carefully. What I want to do is I want to try to have us look at a circular pathway. And so I'll use this as a template, make a circle. Pretty straightforward. Okay. And what I need to do to be able to talk about this intelligently is I have to impose a coordinate system. So I'm going to have an X and a Y axis here, and I'm just going to try to get those drawn in. Simple and fast, effective. There, good enough. Okay. And so we have a circular pathway. Now keep this in mind. I have a complete circle here. The pathway doesn't have to be circular. I might have a car, for example, going through a right-hand turn. So if you can imagine a car headed, say, northbound, and just makes a right-hand turn, and then now it's headed eastbound, and it just continues straight. So the part of a circle there would be this quarter of the circle in that right-hand turn. And during the turn, the path is still circular, even though you don't complete one full circle. So keep that in mind. It doesn't mean that it has to be a full circle. But what I'm going to do first is analyze this, and I'm going to say, well, I have an object. Here's the center of the circle. Here's where the object is at this moment in time. And this object currently is headed in this direction. So there is an initial velocity there, right? And then sometime later, the object is here. And when it's here, the object is headed in this direction. So there will be a final velocity. So look at this. If I've drawn those two arrows the same length, then speed has remained constant. Speed is constant, but the direction has changed, and therefore there is a delta V. There's a change in velocity, and I want to show that to you. So to accomplish this, what I'm going to do is take this arrow and I'm going to copy it, and I'm simply going to redraw it from here, right there, starting at the same spot that this one started at. So I take that and just imagine drawing it here, right there. So there I have copied final velocity to this location from this location. And it seems weird, but I'm allowed to do that. I have not changed the length of the arrow. I have not changed its direction. It is the same velocity here and here. The cool part about this is now I can analyze what is the difference in these two velocities. Because recall, any delta something or other, so I have a delta velocity, but a delta is equal to a final minus an initial. So my delta V is equal to final velocity minus initial velocity. I'm not going to do this with numbers, but I need to look at the difference between these two. And in order to see that, what I'm going to do is go from the end of the initial to the end of the final. And that will show me the delta V. Okay. So here's the trick. As the object went from this location over to this location, at no time was it headed toward the center of the circle, right? That should make sense. But the change in velocity is headed toward the center of the circle. And here's the neat thing. Wherever the change in velocity is headed, that is where the acceleration is headed. So the question is going to become that, of course, you notice the delta V is headed toward the center of the circle. That's the change in velocity, right? It's pointed at the center. Will it always be pointed at the center? Will this always be the case? Well, what's going to happen when we look at the object down here? So it will now be headed in this direction. That's a new final velocity, and here was the original. Now this is really going to be called an initial compared to that final. And again, what I want to do is I want to take my final and I want to copy it and put it here. And so they're both initial and final starting at the same location. So there's the copy of the final velocity. I've simply copied it from there to there. And I can look at something happening. I go from this one to that one, and I have the delta V. And again, it is still pointed toward the center. So yes, the answer is yes. The delta V will always be pointed toward the center. And what that means is your acceleration will always be pointed toward the center. So let's lay this out. So there must be an acceleration that points in the direction of delta V. They must be going in the same direction. Now notice I didn't draw the blue arrow for acceleration as long as that. Well, I don't know that it will be as long as that. There's no way of knowing its length, not from a diagram. But I can certainly identify the direction, and the direction here as well, and the direction anywhere. And since the delta V will always be pointed toward the center, the acceleration will always be pointed toward the center. This is for an object moving in a circular pathway at constant speed, right? The acceleration is always pointed or aimed, pointed, not painted, oh my goodness, pointed toward the center of the circle. Always pointed toward the center of the circle if it's moving at constant speed while it's going through that circular pathway. All right, now here's the next step, the next connection we are going to make. If there is an acceleration here, of course there has to be a net force. We already said that, right? If there's an acceleration, there must be that net force. Here we go. So kind of following along the lines of this argument for the acceleration, we have to say that the net force will always point in the direction of the acceleration. Always. The two are tied together. They're both vectors. The direction totally matters. So, what I have going on is I can say, look, okay, I found the direction of the delta V. I found the direction of the acceleration. Therefore, on average, I found the direction of the net force. From here to here, between those two locations, the net force is aimed toward the center of the circle. From here to here, the net force is also aimed toward the center of the circle. Always. It doesn't matter where the object is, as long as it's traveling around the circular path, then it's always, the net force is always going to be pointed at the center of the circle as it travels around. That's super important to realize. So, therefore, the three dots, if you haven't seen those before, that means therefore. Therefore, both acceleration and net force point toward the center of the circle at all times. So that's an important statement. Something real important to understand. The direction of the acceleration, the direction of the net force will always be toward the center of the circle for any object that is moving in what's called uniform circular motion, or moving in a circle at a constant speed. Okay. Now, got the foundation laid down for understanding this acceleration and this net force. But there's a little bit of terminology we want to learn. So, page 3. We have this acceleration. This acceleration has a name. It's called centripetal. That's T. Acceleration. Sorry, centripetal acceleration. All right, that's an important word, centripetal acceleration. And you'll see the symbol in your textbook, A with the subscript C. Now, occasionally you may see me slip up and write ACP. And that's simply because in the textbook for the AP Physics, the symbol is ACP for centripetal acceleration. So either one is acceptable, no big deal. Now, what is this acceleration equal to? So, your textbook goes into a little bit of math leading up to this equation. So, centripetal acceleration equals. I'm not going to get into that math that's behind this. I'm going to just kind of go with it. Centripetal acceleration is equal to v squared over r, where v is the speed, darken that a little bit, and r is the radius of the circle. So if we look back at this situation, we can say, well, the speed is the same all the way around. So the speed there is the same as the speed there is the same as the speed there. And so constant speed, whatever that speed is, it's v. But we also want to recognize that there is a distance here. Let me use this color. This distance r, this radius of the circle. That totally matters in this equation. So centripetal acceleration is equal to speed squared divided by the radius, right? Awesome. Well, let's go back and look at that situation with the ball and string. So, quick sketch again. Thumb going. Right. And wrist, hand, fingers. All right. So we're holding on to this ball on a string, twirling it around. All right. More or less. You get the idea. And at this location, we have, well, if we wanted to, we could label all kinds of things. But what's important here? We've determined that there is this acceleration toward the center of the circle. If there is an acceleration, remember Newton's second law. Newton's second law says that if there is an acceleration, there must be a net force acting on it. Here we have an acceleration. So that's centripetal acceleration there. And therefore there must be this net force. And we know that the net force must be in the same direction as the acceleration, which would be toward the center of the circle. There must be this net force here. It absolutely exists. It has to come from somewhere. So here's the thing about this. This is basically Newton's second law, but applied to an object moving in a circular path. That net force is often called by another name. You might read in the book, or you might hear me say this, it might be called centripetal force. Okay, so there's that word centripetal again. It is very important. Centripetal acceleration, centripetal force. It's a word you want to be very familiar with. And it essentially is just a force toward the center of the circle, and it's what creates the circular pathway that the object is following. That centripetal force is what changes the direction of travel. And that should make sense. You take something, you swing it around your head, and you have to pull on that string, right? So in this example, or in this situation, or other situations like this, that force, that net force is provided by tension in the string, is it not? So really, we're talking about force of tension, right? But you got to watch out. You please pay attention, because that net force, in this case, it's obvious where it comes from. What creates it is tension in the string. That force must always be there, though, even if it's not obvious where it comes from. If you don't see a string, there still must be a force there causing the motion to be moving in a circle. Has to be there. Absolutely must be there. You're changing velocity because you're changing direction. You're changing velocity means you're accelerating. Acceleration means there is a net force. So for example, here's one situation where it may not be absolutely obvious at first what's going on. So, for example, let's say you're in a car and you're headed northbound, and so you got the road, there's your car, and you are going in that direction. And you're going to change directions. You're going to make a right-hand turn. And so the roadway, of course, is going to curve, right? And to accommodate your desire to go a different direction. And so you make this nice right-hand turn, and you're going straight to the east, continuing on your merry way. Little dashed line down the middle of the road, keep cars on the proper side of the street, no head-on collisions, all those kinds of things. So, okay, that's all well and good. Now, what does this mean, though? When you look at this, the car is traveling through a portion of a circle. So there must be a radius to this portion of the circle. The radius would be in the very center. I'm just going to eyeball it right there. And I can mark that if I want. So there, and basically I have a quarter of a circle, but there's a radius right there. Now here's the trick. So if I wanted to identify it, I could say, well, you know what? Are you sure it's a circle? Well, apart from holding the roll of tape here during the video, you just imagine the rest of this being there. Here's the rest of the circle, and essentially the roadway has its own curve in it, right? Draw that in. Just kind of swing that around, just a little bit, but you get the idea. And you got the dotted line of paint in the center. There you go. So you can see, you really can see the circle now. Even though the path itself is not a complete circle, part of it is circular here. That's very important to you got to be okay with that. You have to accept that. But here's the issue, right? During the turn, it's when the car, say, begins the turn, there is all of a sudden a net force pulling toward the center of the circle. What creates that force? What is causing the car to turn? No, you cannot say the steering wheel. No. There has to be something external to the car that is a force affecting it, that is an unbalanced force. So what would that be? Well, it turns out in this case, friction, our good friend. So there's no tether, there's no rope or cable or anything tying the car to a pole here in the center. And without all of that, the car still manages to change its direction. So this force that's doing that change in direction, in this case, comes from friction. Now, if you really understood friction, you would realize that this is static friction force, hopefully, as the car rolls around. Hopefully the tires are not skidding across the pavement. We have static friction, even though the car is moving. So pay attention. Sometimes the source of this centripetal force or this net force is not an obvious source. But now, bringing it all together, what we know is that there's a net force. Net forces will cause an acceleration. We also know, and this is just general, this is Newton's second law of motion right here in a nutshell, but we also know that a centripetal acceleration is related to the speed squared divided by the radius of the circle. And so we can put those together, so we can say, therefore, for what's called uniform, and what that means is constant speed, uniform circular motion, then the net force will be equal to the mass times the centripetal acceleration. But the centripetal acceleration is equal to this business here, so I can simply make that substitution. So the net force acting on the object moving in a circle is equal to the mass times the speed squared divided by the radius. And so this is a very important relationship that you want to know, and you want to be able to work with it. So, you know what, I should remain consistent for you guys. This was page 4 of these notes in the video. Now, this is all well and good. This is a very simple equation that you can work with, and the idea of swinging something around in a circle is an easy one to imagine and deal with, right? But there's something else to consider. I've been saying words like centripetal acceleration, centripetal force. And those are words you may not have heard before. And I understand that. There's another word that I'm sure you have heard before. And we have to spend a moment talking about that. And the other word you have heard I get this question a lot, and it's a good question.